Hello. Okay, so let's get started. So share screen. So, okay, so hopefully, okay, sharing screen, right? Okay, so let's go Notability. Okay, so today we will go more on uniform convergence. So, really quickly, some facts about integrals. So hopefully this is all clear. So if GH integrable, so this should be review, math 2b. G of x is less than or equal to h of x for all x in AB, then the area under the curve of G is smaller than the area under the curve of H, right? So basically, if H is always above G, when you take the area under the curve, it's clear H is bigger. So next, if G is integrable, so no, not every function is integrable on AB, then we have this, right? So the absolute value on the outside is less than if you bring the absolute value to the inside. So, and a thing to note, at least for us, is continuous functions are on closed intervals, sorry. On closed intervals are integrable. Intervals are integrable. So here comes the big theorem, right? So Fn continuous functions and on AB, and Fn goes to F uniformly on AB, then limit n goes to infinity, AB Fn of x dx is integral AB f of x. So note, without the star, I can't write this, right? Without this part, because here, Fn, we're assuming it's continuous, so it's integrable. And we had a theorem before that says if a sequence of continuous functions converge uniformly to a function f is continuous, right? So f is integrable. So we could write the right-hand side of the equality. So really, this is two things, right? So they sort of skip the step, but they basically say you can bring the limit inside, right? And we have the Fn goes to f, so this is f. So they really skip the step, but yeah. Okay, so now we have, just like, remember, for pointwise convergence, we had that, Fn goes to f pointwise if and only if Fn was Cauchy, right? We sort of had like a Cauchy criterion. So similarly, for uniform convergence, we have something similar. So let me define what it means to be uniformly Cauchy. So Fn functions on a set S and R and is uniformly Cauchy on S if and only if for all epsilon greater than 0 there exists n such that for I'm gonna start using the convention that we're bigger. Yeah, mn bigger than n, fn of x minus fm of x is less than epsilon, and this holds for all x and s, right? So that's the uniform part. So my n, my capital N, does not depend on what x is. Okay, so again, there's just like pointwise, there's a theorem that says fn sequence uniformly Cauchy. That on S and R, then there exists F such that Fn goes to F uniformly, right? So kind of like the statement here, but for uniform. And similarly, you know, you can show the other way. So if Fn goes to F uniformly, because remember, this part was if and only if, right? So if Fn goes to F uniformly, then Fn is uniformly Cauchy. In fact, the proof of this and the pointwise part is pretty much the same. It just depends where you put the for all x and s. So the proof is pretty much word for word almost. So, okay, so quick question, why is this important? So why do we need another definition for convergence, right? Because from this theorem, they're equivalent. So why do we care about this Cauchy definition over like a uniform, like the other definition, right? For example, like forget uniform, right? What we had a definition here, right? So the question is, why care about this? If these were the same, right? It's if and only if. So does anyone know? So let me see who's here. Oh, a lot of people. Okay. So who knows? Like why do we like this Cauchy definition over some other one? I mean, over the other one? Because if they're the same, like it seems like there's no point, right? Anyone want to give it a shot? No?
Is it because you don't need to know the limit?
Exactly. So Cauchy, you see Cauchy, it only involves terms in here, right? You don't need to know what f is. So, and more importantly, so Cauchy, you know, like if you, because you know, like sometimes if I give you a sequence, if you don't know what the limit is, it's impossible to use the limit definition, right? Because you need to do fn minus f. So if you don't know what f is, it's sort of impossible, right? But Cauchy criterion basically lets you say, okay, I don't know what f is, but I don't need to. I just need to check, you know, the terms in the sequence itself are close to each other. But no, Cauchy, if you show something's Cauchy, you will get it converges, right? But you still won't know what f is. So the you know, the counter to this is it tells you less, right? So it'll just tell you the sequence converges or converges uniformly, but you don't know what it is. So, okay. Let's continue. So there is this theorem for series. It's really a repeat of the old theorem, but let me just write it. You'll see what I mean. So sum k equals 0 to infinity gk functions on set S in R such that gk is continuous on S for all k. And so this is like gk of x, right? And series converges uniformly on S. then sum k equals 0 to infinity, gk is continuous function. So this is pretty much immediate, right? Because this thing's the limit, right? This thing by definition is, the sequence of partial, like the limit of the sequence of partial sums, right? So if you have k equals 0 to n, gk, this is like your, I'll call it fn, yeah? So your fn is like this, right? And fn goes to, this thing, right? And each fn, since each gk is continuous, and you have a finite sum, right? The important thing is finite sum. This only, sorry, well, what happened? This should be capital N. So this is a finite sum, right? So if you add two functions, right? Two continuous functions, it's still continuous, right? You might not know if you add infinitely many, right? That's the whole point. But if you add finitely many, it's certainly continuous, right? So each of these are continuous, and you're assuming that it converges uniformly, right? This thing is uniform, so the limiting function is continuous, right? I mean, it's just a repeat of that old theorem, right? A sequence of continuous functions that converge uniformly. The limit is continuous. So, but this is just the wording for series, right? In this case, your sequence is like a finite sum of continuous functions. So okay, so this theorem is not really that important. So the real important one is this one, Weierstrass. In fact, it's the proof of this, but so if there exists MK, a sequence of non-negative real numbers where some MK is less than infinity, then and if your GK, so note your GKs, the bound is bounded by MK. So G1 is bounded by M1, G2 is bounded by M2. So like the bounds can change for each term in your sequence. For all X and S, then some GK converges uniformly on S. So let me just say the idea is, this thing is less than or equal to this thing, which is less than infinity, right? So, and this thing doesn't depend on S. Doesn't depend on S. So, sorry, should be this. I mean, on X and S, right? This thing is just a sequence of numbers that depends on K, right? So you can see convergence is uniform because there's no dependent on X, right? So I'm pretty sure your professor should have proved this, but if not, we'll be sort of going over how that proof is done when we go to like when we start doing the book problems. But any questions so far? Okay, so 25.5, let's start doing questions because I feel that's the best way to learn. So Fn, sequence of bounded functions on a set S, and Fn goes to F uniformly on S. Prove that F is a bounded function. So I just need to show that, so Fn, let me write the question first, sequence of bounded functions. So let me just write it like this, right? Fn of X less than or equal to Mn for all X in S, right? Sequence of bounded functions on S. So note N can change, right? It never said they were bounded by the same number, right? So F1 could be bounded by 5. F2 could be bounded by like 8 or something, but it doesn't need to be the same. And Fn goes to F uniformly. Show F is bounded. So I just need to show f of x is less than or equal to some number for all x and s, right? So I just need to show this. So how are we going to do this? Well, basically what we're going to say is we have a bound, right? We have this thing. So let's let epsilon be 1. Then since, fn goes to f uniformly, right? There's some n such that, so epsilon being 1, you could have chose it to be 2 or whatever, right? It doesn't matter. So there exists n such that for n bigger than n, this thing is small, right? That's what it means to converge uniform. In my case, epsilon was 1, so, right? So let's let n naught be bigger than n. So n naught is just any number bigger than n. I just need 1. Then f of x is what? So this is another, you'll see this trick a lot in real analysis. You subtract one term and you add the same term, right? Now, this is by triangle inequality, less than or equal to this, right? So here, what do we get? So basically, this part is less than 1, right? Because n naught's bigger than n. So from the top, we get that this is less than 1. And this thing, by assumption, right here, right here, is less than the number m n naught. So f of x is bounded by less than or equal to 1 plus mn naught, and then you're done, right? Mn naught is some fixed number, and I don't care what it is, and so you're bounded by like some number, right? Yeah, so you see epsilon did matter, right? You could have chose epsilon to be any number. It's just that your n will change, your capital N will change. So, okay. So let me just note this. So in fact, you have something better for uniform. So fn of x, the sequence itself is uniformly bounded. So what does that mean, right? So what I mean is fn of x is less than or equal to m for all n and for all x, right? Oh, sorry, yeah. So basically before, each fn was bounded by some number, right? So f1 was bounded by m1, f2 was bounded by m2, but I'm saying there's one number where all of them are bounded by it. So let's sort of see this. So the idea, you should, I feel you should just take note of the idea. So the idea is limit gets rid of infinite part, right? Because we sort of have, for limit definition, like n bigger than n, right? This thing has infinitely many terms, right? This thing infinite. And then for finite part, just take max. I don't care what it is, but I mean, if it's finite, you could certainly just take the maximum, right? So the idea is if we just take epsilon equals 1 and n as above, then for n bigger than n, right? I have that this is true, right? So again, same property, triangle inequality. But this time, I'm going to go all the way up to n plus 1, right? So it's n plus 1 because it's n bigger than n. So your first n is like n plus 1. So triangle inequality is this, right? Now this is less than 1. This is less than 1, right? Because capital N plus 1 is certainly bigger than capital N. And this thing is by assumption less than capital this thing, right? N plus 1. So this is less than or equal to 2 plus capital N plus 1, right? And this is, so let me just put this down, right? For N bigger than N, right? This is true. Now, what about, so that's the infinite part. But I need to show this holds for all N, right? So I haven't shown that. I only showed the infinite parts, but what about finite part, right? What about N less than or equal to N? Well, the point is there's finitely many. So we have that, and remember, we always have this is true, right? Always. So basically this thing is just bounded by the maximum of this bound and the finite part, right? I mean, there's only finitely numbers less than n, less than or equal to n, right? So less than m1, m2, m3, all the way to mn, right? And the max will be your number. So yeah, so in fact, your fn's are actually uniformly bounded. But for the question 25.5, you just needed that it was bounded. But I'm just saying, a cool thing is that it's actually bounded by a fixed number that doesn't depend on x or n. Okay. Any questions so far? Okay. So let's go over 25.9. So let a 0 less than a less than 1. Show it converges uniformly on negative a to a 2, 1 over 1 minus x. So can I trust you can all do part A? So I mean, okay, so let me see. Do I want to? Okay, well, yeah, let's just do this. So 0 less than a less than 1 to infinity x to the n converges uniformly on negative a to a 2. Okay, so can we all agree that we know it converges to 1 over 1 minus x? Yeah, I trust you all know the geometric series, right? So let's just check that it converges, the convergence is uniform. So how are we going to do this? So what we're going to notice is this is going to be, so that the quick way is to use the Weierstrass m-test. So if I go back up, right, some mk sequence of non-negative real numbers, and we have that absolute value gk of x is less than or equal to mk. So in this case, my mk is what? So, or mn, right? So here, gn of x is x to the n, and my mn is a to the n, right? So we have that on, in this case, absolute value x to the n, right, is certainly less than or equal to a to the n, right? If we're considering x in, right, for x in negative a to a, right? The biggest number is certainly a. So here, and we have that, and sum a to the n converges, right? As 0 less than a less than 1, right? This is geometric series, right? So we have that sum xn converges uniformly by Weierstrass M test. So let me sort of, so it seems that I never really, proved Weierstrass M test so let's just see how it works, yeah? And then after I do this once, you'll be convinced that, this whole thing's true. So what we're gonna do is let's do it, explicitly. Let's prove sum n equals 0 to infinity is uniformly Cauchy, right? Another way is to do the other definition, but let's see this uniformly Cauchy thing in action, right? So basically, what I'm gonna do is I know before I prove that, I know sum an n equals 1 to infinity, sorry, a to the n converges, right? So what does that mean? So one thing you should all know is if a series converges, the tail goes to 0, right? So because, again, what does it mean to converge? It means for all, so for all epsilon bigger than 0, there exists n such that for n bigger than n, sum an n equals 1 to infinity minus sum n equals 1 to n is less than epsilon, right? Because this thing is my fn of x, right? And this thing is like my f of x, right? But this thing, I can rewrite this, right? For series, this is just this thing, right? So everyone agree? Oh, sorry. Sorry. Let me, yeah, I have too much. There we go. So, and then this should be k plus 1. Yeah, I'm using k because I used n for the index of my series. So, yeah. Okay. Sorry about that. Might be a bit confusing, but okay. So this is sort of like the tail, right? This thing's like the tail, because you should think of like k as large, right? And then it goes out to infinity, right? This part is like, because this part, the tail plus this part is the whole thing, right? This thing's like the finite part. And then the bottom is like the infinite tail. So if a series converges, the tail goes to 0, right? So basically, what I'm going to say is less. So I need to show this part. So let's write it out, right? To show sum n equals 0 to infinity x to the n is uniformly Cauchy. So let's write out the definition, right? Want to show for all epsilon bigger than 0, there exists n such that for mn bigger than n, f n of x minus fm of x is less than epsilon, right? So in this case, fn, okay. See, this is why I don't like this. Is it, okay, I'm gonna use k, because again, n is the index for my series right here. So sorry about that. So here, right, fk of x is sum n equals 0, the k is the partial sums, right? So I need to show the terms get small. Okay, so let's show this. So let's let epsilon be bigger than 0. And we're going to use what we had before, right? As sum an converges, tail goes to 0, right? So choose, or there exists n1 such that for k bigger than n1, sum n equals k to infinity, an's less than epsilon, right? That's this part right here. And then we're done because we choose our n to be n1 for mk bigger than n. We have that. What is fk? Fk is this thing minus sum n equals 0 to m x to the n, right? That's fm. Now, without loss of generality, let's assume m smaller than k. If not, we swap it, right? Because it's possible because we have the absolute value, we could just pull out the negative sign. So this is just this, right? So this is just n. If m is the smaller one, it's m to k x to the n, right? Or m plus 1, right? Now this thing, if you remember the properties of a geometric series, this thing is just this, right? I could bring the absolute value inside, but make it smaller. Now this x is smaller than a, right? We're assuming x is in the interval. Again, x is in the interval negative a to a. So here, this is smaller than this. And this is certainly smaller than this, right? Since n plus 1 is bigger than n, this is smaller than. Instead of writing k, I just take it to infinity. And this is less than epsilon, right? By this statement here. Right? For any number bigger than n1, this thing's smaller than epsilon. Well, n plus 1 is bigger than, because n is n1, and I have m is bigger than n. So certainly n plus 1 is bigger than n. Right? So the uniform thing is really just because this thing is independent of x, right? I mean, there's no x here. There's only a number, the number a. So yeah. Okay. So that shows part A. So again, part A, you don't need to write all this, right? You just use Weierstrass m-test. But the proof of Weierstrass m-test is basically this: that the tail goes to 0, and then replace n equals n plus 1 to k to n equals n plus 1 to infinity. That's just the tail, and that's smaller than epsilon. So okay, so let's do part B. What is this? So does the series converge uniformly on -1 to 1? So this is sort of it's sort of something you think will happen, but it doesn't. So if you think about it, negative a to a for all a0 less than a less than 1, this thing approaches this, right? Right? Because what is the open interval -1, 1? This is all the points between -1 and 1. Well, if you take a, if I give you any point in this interval, you could find some a such that it's in this interval, right? You just take, because a is sort of like approaching 1 and -1, right? If you just take a, if a is smaller than 1, you could take a to be like 0.99999, 0.9999, and then negative a is negative 0.9999, so on and so forth, right? So this thing is sort of like going to that open interval. So your first thought would be, hey, if it's true for all A and it's approaching to that interval, then you will think that it converges uniformly. And the point is it doesn't. So let's see why. So sum k equals 0 to n. So is everyone familiar with this? I trust you are all familiar with this, right? So this is sort of like geometric series for like the partial sums, right? It converges to this. I tend to like so let's factor out -1. You don't have to, but I like the x's on the left. So let's just do this. So this factors as this, right? X to the n plus x to the n minus 1, x to the n minus 2, all the way to 1, right? And these cancel. So what you're going to see is this thing is just this thing, right? Now this, right? And if you don't like plug in, right? Because this is x to the 0 plus x to the 1 plus x squared all the way to x to the n. So whichever way you like. So here, this thing is bounded by what? So on -1, 1. X is certainly bounded by 1, right? So this is bounded by 1 plus 1 plus 1, right? Because 1 to any power is 1. And how many times do I have? This thing is equal to what? How many 1s do I have?
And
So you should be careful, right? So if n was 2, it's this. So this is for n equals 2, right? And this is 1 plus 1 plus 1. Right? So you sort of see, because you have the constant term. Your constant term is like x to the 0. And you have to count that. So this is actually just n plus 1 terms, right? Because you sort of have that a0 term. Okay, so this is bounded by n plus 1. So each sequence, right, are partial sums, right? I'll call it f. Oh, I used k. Okay, I can use fn now. Finally, I did something good. So k equals 0 to n, right? They're bounded by mn, right? Which is n plus 1, right, in this case. So from that problem, we just proved the 25.5, right? From 25.5. Let me go back up. Right here. So let me see. Where'd it go? Right? Yeah, 25.5, right? Fn sequence of bounded functions, right? In our case, it was bounded by n plus 1. And Fn goes to F uniformly, then F is bounded, right? So, whoa. So if we assume Fn goes to F uniformly, assume by contradiction, Fn of x goes to 1 over 1 minus x uniformly on -1 to 1. What does 25.5 say? It says f of x is bounded, right? Then f of x is bounded. So then 1 over 1 minus x is bounded on -1, 1. Is this true? Is 1 over 1 minus x bounded on -1 to 1? So it's not when x approaches 1, right? Because when x approaches 1, your denominator is 0, right? Or gets closer and closer to 0. And when you divide by a really small number, you get a really big number. So, but, right, bounded on -1, right? So we get a contradiction, right? So Fn does not go to F uniformly on -1. Yeah. Okay. Any questions on this? So let's do something else. So here, let's do 25.6. Yeah. So if sum AK is less than infinity, right? 5.6. If sum AK is less than infinity, then sum AKX to the K converges uniformly on -1 to 1 to a continuous function, right? So this part A. Let's do part A first. So if you see the first hypothesis, it's basically the hypothesis of Weierstrass M test, right? So almost, at least. Yeah, pretty much it is. So remember, Weierstrass M test, let me go back just to remind everyone so we are all clear. So let's go back. So this is Weierstrass M test, right? So in this case, my MK is my AK. It's exactly this, right? Sum MK is less than infinity. They gave me sum AK was less than infinity. And they took absolute value to get the non-negative part. And we just need to show that this thing is less than or equal to MK, right? Then we converge uniformly, right? So our MK is exactly our like AK right here, right? We have some AK less than infinity. So, and then this is like my GK, right? And certainly this thing is less than or equal to AK for X. Remember, we only care about -1 to 1, right? So certainly this thing which is equal to, AKX to the K. So let me just write this, right? Sum AK, so bad, AK X to the K. This thing's bounded by just AK, right? Because X can be at most 1. And this thing is certainly smaller, and sum AK less than infinity. So this series converges uniformly by Weierstrass M test. Yeah, if there's anything you're gonna remember Weierstrass M test by Weierstrass M test. But so why to a continuous function? So remember, what's that theorem? If a sequence of continuous functions converge uniformly, the limit's continuous. We have the converge uniformly part. We just need to show the sequence is continuous, right? And hopefully it's clear. Sum, K equals 0. Each term is continuous, right? Is continuous. I mean, this is a polynomial, right? Polynomials, i.e., are continuous, right? because this thing is just a0 x to the 0 plus a1 x plus a2 x squared. This is just some polynomial, right? If I cap it at some n. Okay, so limit is continuous. Okay, and part B is pretty much what they have. So part B is, does this represent a continuous function? It's just part A, right? It's part A with, you just need to show that sum AK is less than infinity. In this case, yeah, see, they always swap K and N. So in this case, like AK or AN, A sub N, is 1 over N squared, right? So you just need to check. You just use part A with like, replace AK with like 1 over N squared, right? And it's clear that sum 1 over N squared is less than infinity, right? This is the P series, right, from Math 2B. So what is it, does? Yeah, so the answer is yes. So yes by part A. You just apply part A, right? So note that same thing here, right? 25.7, it's really easy, right? 25.7, you bound it. So again, like 25.7, you have sum n equals 1 to infinity, 1 over n squared cosine of nx. What is my a? So like, this is like my a n. Your an is 1 over n squared, right? It's pretty simple, right? Because, and we have that this thing's bounded by it, right? Because cosine is bounded by just 1, right? So, sorry, my square looks bad, right? And then, so converges uniformly on R by Weierstrass M test. Yeah. Okay. Any questions so far? So let me conclude by saying your quiz is on uniform convergence. Quiz 4 and 5, yeah. So again, quiz 4 is upload, right? Starts 2 p.m. Wednesday to 12:01 a.m. Thursday. And quiz 5 is on Canvas, right? This one you have 2:00 p.m. Wednesday. So this is a bit different, right? You should be careful with this one because it is to 11:59 p.m. Friday. But again, this thing is 1 attempt, and I'm giving 25 minutes, right? It's 4 questions, so for quiz 5. So 4 questions, 1 multiple choice, and 3 true false. Yeah. So I don't think it should be that bad, but yeah, and it's all on uniform convergence. So okay, any questions? So let me go. Yeah. Any questions so far? Let me read the chat. Yeah, it's both on uniform convergence. Okay. Midterm review. Yeah, I don't know, because I mean I don't know how Neil makes the midterms. So and I heard this is the one time. So be aware that it probably won't be like my quizzes. You won't have like 10 hours to do it. So yeah, I'm not sure how it will go.